Good afternoon.
Good afternoon, sir.
Good afternoon. Good afternoon. So we are a little bit late, 1 minute. So recording has started. You may please put your attendance now. Today, we will be discussing, not completely, but we will be starting about, we have already discussed the different component of fermenter, and I will be switching over into three different things. One PPT I will be discussing, I will go into textbook, and one World Health Organization manual. Three things I will come in our discussion today. So first of all, let me go into our textbook part. That will be more easy for me to discuss. I think I have shared my screen. No. Okay, I'm sharing my screen, and we'll go for a quick drive into that. So basically, supporting things will be given in your PPT and all other documents. I will share out of them later. Now, first of all, this chapter is chapter 7. So you must be careful when I'm discussing this. You can always refer to the content more easily. So in this chapters, we will be discussing the design of fermenter, and not only design, we'll be also talking about some operational aspects of fermenter. What should be the content? So basic things about the fermenter design. Last 1 or 2 classes, I already told what are the things is there. There is agitator components, right? We talked about components. We have agitators, we have air supply, air spurger, we have a baffle, okay? We have baffles, we have a solution for pH, we have air supply, temperature, cooling jacket. That makes a fermentation system. In today's class, we will be focusing on not only that, we will also talk about how to make the operation in a fermentation process. And it all depends on very important things. It depends on what is the microorganism you are dealing with, how much precautions we should take. Because there is a lot of chance, there is a lot of possibility that when you are doing some laboratory work using your microorganism, when I am injecting the inoculum, there is a lot of possibilities that microorganism may come out, or the exhaust gas going out of the fermenter, because you are continuously supplying oxygen, right? There is a possibility of exhaust gas also carrying some contaminants. So today we'll summarize very quickly on what is the precautions level we need to have, what are the shape of the fermenter, I mean to say constituent of the fermenter, how is it normally made in lab and an industry. So I will not go through all the lines, you need not really need it, that is unnecessary. So basically, when I am talking about lab scale or moderate scale reactor, they are either, if it is a small scale, we'll put glass, okay, we'll put glass. If it is a moderate size and you need to have more rigid material, we can use stainless steel. So stainless steel and glass, these two are the basic configuration we can have. Sometimes some reactor can have the top plate and bottom base made up of stainless steel. Other components are essentially made up of glass. So glass plus stainless metal formulation is there. Complete glass formulation is not possible because you have to put your all those piping and connections. So some metal is definitely required. So glass plus metal is there, or essentially completely metal. These two domains are mostly different kinds of design of fermentation will happen. So large mild steel cylindrical vessel with hemispherical top and bottoms are constructed, so it can be sterilized with steam under pressure. That is very, very important. That is one problem I will talk. I will make a diagram to discuss with you just for a few more minutes. If you don't understand anything, you can put me to stop so that I can explain. So we are talking about the construction of a bioreactor. Okay. So as I was telling, what are the different kinds of bioreactor we can encounter? Many form. Let me tell you some designs. I'll try to draw diagram. It may not be really very good. So first one is a metal plate. So for example, this is a metal plate. This is a glass vessel, and again metal. This design is there. So this portion, bottom portion is metallic. Top plate is also with, of course, you will have screw and phalanges to lock it up. So this is a cylindrical glass vessel. Okay, and this portion is metallic. Top plate is also metallic. Maybe you are putting some heating or something like that. Heating, cooling coil systems can be there. So this is metal plus metal and glass. Second variant, most widely used in small scale lab. In fact, we also done all those reactor in our lab study, is basically a glass. And top plate is only metal. This is a metal plate. Of course, for standing, you can put some stand, that is different. Okay, just for standing purpose. Stand is there, metal stand. But that is not a part of the fermenter. So this is a fermenter, for example. So here, top plate. And here, semi-spherical bottom. Why semi-spherical bottom is used? Two reasons. The first of all, the adhesion of microorganism is low. It will not stick there. Because if you are having some square-shaped notches are there, if you are having anything sharp 90-degree notches are there, here is a good chance that microorganism and contaminants will deposit. So that is actually avoided in most of the time. We do not make any square connections or joints with 90-degree angle. That is not done essentially. Rather, we can have always a bigger angle. Okay, so maybe 120. Even if I'm having, so you can try to make it smooth and 120 at least. Here also you see, if it is a glass, nothing will adhere there. So it's very easy to clean. So this hemispherical glass is fine. But glass have one problem. You cannot make it high pressure. If I'm putting some aeration, we cannot go very high pressure. Okay, so maybe some 1 atmospheric pressure is good, 1.5 is good. If I'm going to 2 to 10 atmospheric pressure, high pressure, the glass will break. It cannot really withstand. So that is one problem. But glass is actually comparatively cheaper in comparison to the stainless steel material. So this is one aspect. Third aspect is that completely glass not possible. The third aspect is that no, okay, we will make it completely metal. Metal means, of course, we can have mild steel or stainless steel material. And if I'm going to make completely metal, then many people prefer both top and bottom hemispherical. Okay, like a dome. Industrial fermenter are like that. Okay, you can have connection to hold it, holding platform, that is fine. We can have aeration and agitation through this metal driving itself. We can have air supply, but completely made up of metal. The advantage is that, two advantages. We can sterilize it when I'm making the food. I'm putting all the ingredients or nutrients and I'm passing steam through it. It is possible. I can pass steam through it and it is automatically sterilized in situ. You see, if it is some 60 meter cube, large fermenter like a house, you cannot really move them and put in a autoclave, right? It is not possible. So it should have in situ sterilization. So hot steam is coming in and it is getting condensed. If it is you are permitting, then it can go out also if you permit it. If you don't permit, then possibly no. So entire system is having cooling, heating, sterilization together. These are all made up of stainless steel. Stainless steel normally contains some around 3% of chromium we can have, but in some cases we can go some 10 to 15% of chromium also. The reason why stainless steel is useful, stainless steel have few properties. The stainless steel chromium is resistance for aberration. So everything is moving, right? So there will be no scratch on the steel surface inside. So it is more resistance. It can withstand much higher pressure and tensile strength is much higher. So if I go for stainless steel module, It is always preferable when I am looking for fermentation process. So now if I ask you very few questions and very simple things, what design I will prefer? Semi-spherical at the end. What material I will prefer? Stainless steel. What is the advantage? High pressure sterilization. We can have big size pressurization is possible. If I'm making glass, metal glass, this is very not good idea. It is costly also, because 2 metal plates is making it costly, and this glass is in fact more cheaper. So most lab I will have these variants in most of the research lab. So this is about talking about what are the components we should have. Apart from that also, there is some design aspects that we will not talk now, we'll talk it later. Reactor must have a design conformity. What I mean to say, for example, you are running a lab reactor, right? So if I say this is a reactor vessel, try to understand. I'm drawing like a square only. And for example, this is my agitators. I can have more than one agitator blade, depending on how thick, I mean to say how much deep is there. So basically, this dimension, for example, this is diameter of the vessel, right? Inside diameter. This is height of the vessel. And similarly, I can give some name. For example, this is impeller diameter, for example, D prime. This distance I can say, for example, X. This distance I can say Y. This distance I am saying Z. Please try to understand, if I am talking about any reactor, if it is very small or very big, there is always a dimensional consistency. What do you mean by dimensional consistency? I mean, for example, I want to have a big reactor. Then how I will change that? I will change the things in a proportion. That is very important when I am going for a bigger fermenter, when I am going for a big size. The dimension is mostly maintained. You will never find a fermenter where diameter is more bigger than its height. Normally in industry you will not find that. So height to diameter, for example, height to diameter ratio is mostly greater than 1, 1.2, 1.3, 1.5. So this dimension is always defined. Okay, are you getting this point what I am talking? Most of the time industrial fermentation, they mostly follow some reference number, height to diameter ratio, for example. Similarly, I can say this diameter, impeller diameter to main diameter, so D prime by D, it can be around 0.25 to 0.5 normally. So this impeller should not be so big impeller nobody will use. Are you understanding? So impeller diameter, when I am using baffle diameter, how many baffles I should have? 1, 2, 3. These all dimension at what height I will have. So Z by D, all ratio. I'm not telling you the number. All ratio, Z by D or X by Y or D prime by Y. They mostly try to maintain a consistent ratio. These are called bioreactor consistency parameter or design parameter, design aspect, we can normally say. And when I'm having a bigger fermenter, we look like this fermenter I want to make a big. That means, for example, I'm making we can say we are increasing the dimension of this picture in such a way that every aspect enlarges. Like you are making some small Xerox to big size Xerox. Okay, micro Xerox to mega Xerox. That means all dimension will increase. Not only simply I will stretch height or diameter, not like that. That means ratio, those ratio are normally kept constant when I am going for small to a moderate scale bioreactor system. That is all basically basic things. I'll come to your textbook also for some time so that you can track it out. So basically when I am talking about a reactor, we should also understand what material we can have. What should be the basic functions of a fermenter for microbial culture? What is the basic expectation from you? I already talked about that, so I will not speak much. We need aseptic condition for large number of days. Very important. Many times our fermentation can go for 7 days and 10 days also. Nothing surprise on that. Even some cases nearly month. So 1 month you have to grow the culture and it should not get contaminated. So that is very, very important. I need to have adequate aeration and agitation. These two are very basic. Some other criteria you can highlight it one, you can see power consumption should be small, pH should be controlled, it should have some design variables should be maintained, evaporation loss maybe should not be so high. That means you are not so much agitating that water is getting evaporated. So these things you need to always keep into consideration. Are you getting the point? So you can just very basic things, I need not speak on that. It should have always a range in that may be restricted because of contamination regulation, constructed with smooth internal surface. I already told you can have chromium and nickel, we can put it so that the interior surface becomes smooth and it does not really cause much problems, particularly for adhesion of biomass. Other parameters are not so really important, you can go. And this is talking about the basic dimension, right? I talked about the bioreactor already. This is height, for example, of a fermenter. This is liquid layer height. This is, for example, diameter of the reactor. This is diameter of the blades. This is inoculation. This is sampling port. This is air supply. This is baffle. So all the dimension will be actually controlled. You can see here this diagram. They are giving some name. I don't bother about the name. But my point of discussion in this class is that we should understand that all aspect ratio are mostly fixed in most of the industrial bioreactor systems. They do not vary much. Okay, some changes may be there, but they do not go much established differences on the changes in this process. Okay, so these things are requirement. Now, when I am going for aseptic operation and containment, you need to know, that is another discussion I will have in today. So basically, our focus is what kind of material you can have, what dimension you should have, and we should also talk about containment. Containment. What do you mean by containment is restricting escape of microorganism or contamination. Both are very important. You try to understand, we are normally talking that, okay, your media should be sterile, it should not get contaminated. Okay, I understand. That is required when I am doing fermentation. But sometimes we are also dealing with some organism which can be pathogen. Many fermentation process, we are using different kinds of fungi. Fungi can be pathogenic for human also. So not only we need to keep the fermentation process as sterile. Sterile means for media itself I am talking. Containment means whatever microorganism you are dealing, because you are the researcher in the lab, and for example there is air supplies there, air is coming out also. Okay, air is coming out, and if this is a pathogenic one, this will be very much difficult for you, too dangerous. So there is always some regulations and biosafety protocols, which I will definitely share you with some study material. But before that, you try to understand how the microorganisms are basically classified. All the systems, all the containment process, how are they classified? Basically, they are classified based on how large is the scale. It is small scale or large scale. You have to understand small or large scale. Small scale means I am doing in a research lab. Large scale, definitely I am doing in industry. Okay, whether it is small scale, large scale, whether I am taking a microorganism which is genetically engineered or natural. Genetic engineered, you understand, right? We are manipulating the microorganism. And then on pathogenicity, whatever microorganism, is it pathogenic or not? So these are actually driving when I am talking about biosafety norms. Why I am talking these suddenly in bioreactor? Because you are doing the bioreactor operation, and if you know what microorganism I am dealing with, all the protocols for biosafety may change. You have to change the protocol for biosafety. For example, I may not allow to release the gas from the fermenter into your lab. if I am dealing with a pathogen which is contamination level 3 or 4. So there is some biosafety standard, and I will be talking about the 4 different levels which normally people do basically, and that is who recommended biosafety norms. Why? How should I be classifying the microorganism on biosafety class? Okay, we need to have the required safety protocol. I'll talk about what safety protocol later on. First time, let them classify. So I'm talking about B1, B2, B3. I'm talking about the microorganism first. They need B1, B2, B3, B4, 4 class of microbial things I'm talking now. Let me talk how are they. First one, B1, they are low infectious for individual, low infectious for community spread. Are you understanding? For example, you are dealing fermentation of E. coli. E. coli is, of course, it is a pathogen, but it is not so difficult for treatment. So it is not hazardous for the person who are working in the lab. It is neither hazardous that if someone is getting E. coli infection, he will spread to whole country. Not like that. So this is very simple. Not infectious, non-spreading. This one B2. B2 is moderately infectious, but no spreading. Okay, there are many microorganisms which can infect you, but definitely you cannot spread it. So this is low as moderate and no spreading. Third one is pathogenic, very pathogenic for you, but non-spreading. So this is biosafety norms for 3. And biosafety 4 lab is for pathogenic as well as spreading. And you know one example of this at this moment, right? SARS-CoV-2, right? We are already dealing with one in this pandemic, which is infectious as well as spreading. Infection for the person, it is a really danger for the person, as well as it spreads into the community. So depending on what kind of microorganism you are dealing, we can have B1, B2, B3, B4 biosafety protocols in the lab where you are working, in the research lab you are working. So I'll just show you some diagram and some numerical. Just for I'm going to give you preliminary on the pathogenicity of the microorganism. Many things can really change. Your containment level, your sterilization things. For example, if I am dealing with some B4 pathogen, do you think I can take out and sterilize somewhere and I move it? No, it is really dangerous for that. Can I take out the exhaust steam in the room? No, I have to release the even exhaust also through a vent, and it should be filtered. It should not be circulated in the lab itself. The whole air should be circulated out with filtration. So there are many rigidity in the protocol. There is many rigidity in the lab design or maybe the industry design which may be required when I am talking about the containment level. I'll come back to your textbook so that you do not get actually out of the context, and I'll take your example in this textbook portion also. Coming into textbook part, okay, aseptic condition, all those things we will learn. You see, now process organism is the driving force. This textbook is little older one, okay, and because we are taking this textbook version, I will also guide you through WHO website and WHO study material. Not only study material, it is actually a guideline, and I also download and I will share with you. So now classifying whether non-genetically or genetically. Then they are asking hazard allocation, whether it is harmless or it is potentially harmful. Means it is causing problem or non-problem. And then second scale is small scale or large scale. So based on that, they are classifying. If it is a small scale, they put a number A. Large scale, they are putting a number B. And now the hazard allocations, if it is non-genetically engineered, we are giving them a level of containment level of 1, 2, and 3 is required. 1, 2, and 3. If it is going to be non-pathogenic, then I can have a simply good industrial large scale practice I can have. So if it is a industrial scale and non-pathogenic or pathogenic, we can have, if it is non-pathogenic, I can allow GILSP. What is the process? I will talk about later on, not now. It is milder version of industrial process, no so stringency. If it is going for pathogenic group and genetically engineered, the classification, as I told you, B1, B2, B3, B4 are similar. But if it is non-hazardous group, if it is so much pathogenic, my pathogenicity is not there, then we can also have containment level of 1, 2, and 3, not beyond that. So basically, these are the containment level we are discussing. I already discussed with you, so you can just get it idea. Small scale, large scale, A, B, hazardous group 1, potentially harmful group 2. Okay, this is the actually hazard and identification. Here also, we are identifying either it is moderately bigger scale or no hazardous here at all. So we can classify as 1, 2, 3. Here we are classifying as B1, B2, B3, and B4. So these are the two classification scheme we can have. Recent times, actually, that modification has been done. They do not really distinguish between non-engineered or genetically engineered. They put it all together and they make it more simple. That is adapted by World Health Organization. They normally classify as B1, B2, and B3 and B4 classification, and corresponding level of containment is required. Classification I am making for microorganism. Please try to understand. We are talking about microorganism classifying, and to deal with this microorganism, what kind of containment? Containment means what? You are making a change in the process, change in the lab. That is called containment measure. I'll take a very small and very simple example here in your textbook also. You see, okay, first one is GILSP, that is not so pathogenic. Okay, so for that, and containment category 1, 2, 3. So basically, I'm assuming that we are dealing with non-genetically engineered microorganism. So I'm having 1, 2, 3 classification. And if you see how there is different, how the lab working environment is different, you see, basically there is not much difference. If it is non-pathogenic, I do not need any biosafety manuals. If it is pathogenic, I should have biosafety manuals in our lab. You see, in containment 1, 2, and 3, all the 3 category, I should have biosafety manual. And most of them are having common, you see, good occupational hygiene, biohazard sign. You know, biohazard sign, have you seen definitely in recent days, accident reporting, medical surveillance, all those things are common in containment category 1, 2, or 3. It is always there. Even we are having primary containment, operation and equipment if I am talking about. So for example, I am talking about a system. In a closed system, we are doing work microorganism in a closed system. That is, we are normally, for example, we are going to take it up or not. So similarly, basically, I will say containment 1, containment 2, and containment 3 will not be so much different. Only when we are having some minimizing some release. So that's why I am going to minimize and going to prevent, because in many cases, if it is level of 2 and 3, they are more pathogenic. So I have to prevent this. What I have to prevent? I have to prevent release of the microorganism. Yes. In first case, because it is not so pathogenic, I can just minimize. So minimize, prevent. And if I am going to do in a lab condition, that is GILSP condition, I have no restriction. You can just leave it. It is not so stringency. Mostly they do not differ. What I will talk about, how the lab will differ, it will come to know over here. You see, protective clothing appropriate to risk category, everywhere it is there. Changing and washing facilities, everywhere it will be there. But now, from here, when I'm talking about category 1, what is the additional things I'm having? I should have a disinfection facilities that is required. In our lab, it is not required. In our lab, for example, research lab, it is not mandatory that I should have a disinfection facilities. I can have a disinfection facility in some other place, okay, not in the same lab. But when I'm going to come into this biosafety's containment level for 1, 2, and 3, then I should be cautious. I must have in all the scenarios. See, so basically, we should have higher grade of preparedness, higher grade of safety concerns when we are really dealing with the more pathogenic variants of microorganism. What are the things slowly increasing? You see, First one, I only need disinfection. Second one, I need to have emergency shower. Only very cases I can have shower facilities in those places. Why emergency shower? Because sometimes the person who are dealing with this pathogen, or maybe some, not only pathogen, it also deals with someone dealing with some toxic chemicals. So we can really clean the person immediately. So we can have emergency shower attached in your laboratory space. So possibly when I'm having B1 lab, when it is there, then I don't need it, but B2, B3, I must have all those components available there. So basically you see at increasing grades of facility requirement may be there. You see, last one you see, area hermetically sealable. Hermetically sealable means you cannot have any passage of air or water in the total containment. It is not like a room, it's like a chamber which is airtight, watertight. So that is also required when someone is dealing or someone is going to prepare dealing with microorganism of B4, and containment level requirement is 3. Third level of containment is desired. So you need to understand how much precaution we should take, how much emergency facilities we should have. We need to decontaminate the effluent also. What is coming out of the lab, not drainage, that also may be required for disinfection if I'm going for containment level 2 and 3. The top 2 levels it may be required. So basically, this is definitely going to deal with only theory. But how we are going to deal with, how I am going to categorize this containment in facilities, how the fermenter will do the job, that is also very, very important. How can I take out the sample without any problem? I'll show you some other diagrams, not here. This looks like we have used similar kind of fermenter in our lab. So how we are taking the samples, how we will allow the inoculation, those aspects, considering these kinds of precaution, how can I deal with them is actually available, or we can have the facility in a fermentation or fermenter also. We should also follow the same procedure when I am going to adapt this in a fermenter. So overall fermentation is what you need to have necessary to consider the procedure to be used, how I am going to take sample, if I am working with a pathogen level B1, B2, B3, B4, in which lab I should do, what kind of fermenter I should use, how should I take the sample, all those things really matters, and we need to understand those aspects when I am going to get for containment category. Body construction I already told, so you need not, you understand, top lens carrying plate, so glass plus metal, or I can have completely metal stainless steel vessel is also possible. So these are the normally, you see some diagram you can study. This is both top and bottom metal plates. Okay, understand? So this is used for heating and cooling also, some metal framework. These kind of reactors are not so cheaper, but we can have a completely glass vessel, more cheaper available version is there. Top plate is mostly metallic plate. You cannot have glass, and we need to have the air sealing, I mean to say O-ring phalanges should be there so that you can make it airtight. So these components will be discussing further in our later class. These components I will discuss later. But before that, okay, these things I will talk later. But before that, I would also like to take you to, okay, this is World Health Organization Laboratory Safety Manuals. Okay, it is from 2004, has been activated. I'll just show you some diagram, I think. Laboratory, for example, basic laboratory, biosafety level 1, 2, biosafety level 3, and biosafety level 4. I think I'll just go there and show you some picture. Now you see summary of biosafety level. I think you can see my screen, right? Summary of biosafety level. What do we need to have? Isolation of laboratory is required. Biosafety level 1, no. 3, 4, yes. What does it mean? It means that if I am dealing, if I, for example, our institute or our industry wants to deal, if I want to deal with coronavirus, for example, someone is going to do, he is likely to have, or she is likely to have, follow biosafety level 4. 4 level biosafety he has to follow. Then what is requirement? Isolation of laboratory. That means what microbiology lab we are having now. If someone is doing this coronavirus culture and he's going to study, he cannot do there. He should have a totally isolation laboratory may be required. Room sealable from decontamination, and okay, sometimes room is completely sealed and we can have, but particularly in industrial actually see, not in research lab rather. So they can have a decontamination, fumigation. So there is a pipeline for fumigation, like air cons we are having, centralized air conditioning we have. Similarly, you can have parallel lines for fumigating the room. So you will come out, all doors can be closed, sealed, and we can start fumigating the room, entire room. It may be required. This facility is only required for 3 and 4. It is not really always there. HEPA filter we will have for air exhaust. What is coming out also we need to treat. That is only required for biosafety level 4. These things you see, double door. In our lab, if you visit, you will see only one door entry. But if I'm going for 3 and 4, I should have double door entry. Now, okay, forget about it. You can read it yourself. I need not read for you. I'm just going to show you the schematics. Good diagram. You should always have biohazard signs when I'm dealing with 1, 2, and 3 or 4 level of pathogens. This is laboratory 1, biosafety level 1. This is actually, I think you can see my screen also. This is typically our lab. If you come to our lab sometime in future, you will see this is like our lab. We have the bench here. I'm having one gate entry. We can have windows maybe closed. We have refrigerator and other instruments are there. And we can have also here airflow cabinets like laminar airflow systems. Vertical system it is showing. But basically that is no much precautions are there. People should be using definitely gloves, decontaminating solutions should be there, and disposable identified with your contaminants you can put in a biohazards contaminants bags can be there. Okay, so this is what I'm looking for. This thing you see outside, we can also have facilities for showering, but it may not be really necessary for biosafety level 1, the design. Just see the diagram. If it is biosafety level 2, you see we have a classification of, for example, radioactive and toxic hazards and non-radioactive hazards. We have to have a classification. This one change will be there when I'm going for another level. We should also have vent. Sometimes some material will cause exhaust fume. Many times we are dealing with some exhaust fume. Sometimes we are drying, centrifuging. So some fumigation will come up. I mean to say some aerosol will be formed. When I'm shaking some culture, some aerosol, air will come. But for dealing that, we need to have exhaust vent. Under that only will do. For in laboratory chemical also, we have those facilities. When I'm dealing with some laboratory chemical which can be toxic or causing fume, I can have this exhaust system and I will do the work there only. So classification and this preparedness may be required additionally when I am going for that. Of course, air exhaust system and these things is also required when I am going to go for safety level 2. You can see what are the components I am going to have. You see, pipetting aid, very small things. It is good for you to study. Avoid mouth pipetting. That is always, even biosafety level 1 also we do not allow them to use mouth pipetting. So basically, this is talking about what kind of precaution and protocols you will be using. Today, I'm just finishing it right now. In next class, and of course, I will suggest you to go through the other B3 and B4 also. But B3, B4 we do not have in our lab system. But in industry, it may be definitely required. Now you see the B3, how much difference? I am having one door here, you see, door plan, one door, common space, another door. My lab is not there. I'm going inside another door and I'm going into the lab. So I have to cross at least 2 doors are there. In third, I am having the shower itself, you see, in my attached inside the lab. Shower is already there. Classification of the compounds and hazards are already there. Whatever we have learned here is already available. Exhaust from the room is actually taken out. air actually is being circulated through the exhaust system, not inside the room itself. So depending on stringency and contingency you may require. Of course, you can see the personal wearing protective gears. These are also a requirement when someone is dealing with pathogens of level 3, or maybe more stringency can be available in the level 4. I'll stop it because we are going out of time now. So basically, if I hope you understood the basic requirement, the basic distinction of different containment level. You can study for more detail. I need not really read for you. So this is the things for our discussion today. Next day, I will talk that, okay, in fermenter itself, how we are going to take those precautions. Okay. Any questions from your side? If you have anything, you may please ask me now. Any questions from anyone?